Hello, my name is Dmitry Soshnikov, and this is Functional and Logic Programming course. Today we'll dive deeper into functional programming, starting with some language features and talking about recursion, and then going deeper into relations with lambda-calculus, different computational orders, and those kind of things. So let's start by revisiting the function that calculates factorial through a more generic function called iter, which we talked about during our last lecture. So I would remind you that we, using the iter function, we defined a lot of other things like x to the power of n, factorial, and so on. So this iter function was a generic kind of iteration, and factorial is just one specific case of it. So this definition of factorial is based on integers, and that is the reason it cannot compute factorials for large numbers. So if we try it now, so let me define this factorial. Factorial 7, of course, is calculated correctly, but if I want to calculate something like factorial 20, you will see that the result becomes negative. Negative means that we had the case of integer overflow. So what if we want to define factorials for bigger numbers? Luckily, F# supports type called big integer. This is the generic .NET type, so we can use it from F# as well. So what I need to do here, I need to open system.numerics, which is the namespace which contains this type. And luckily, I can take the advantage of so-called polymorphism. This function iter, it takes the iteration itself happens on integer numbers because we use a+1 here, but the accumulator can be of arbitrary type, and this is indicated here because Visual Studio Code, it shows us the type signature of the function, and you can see that this type of accumulator, which is transformed on each step, is arbitrary. So we can convert this function to use big integers by starting our accumulator from 1. 1I means a big integer 1. And then I need to adjust the operator, because multiplication operator would not be able to figure out automatically the type conversion between two different types. And that's why I would need to replace this function by a manual definition. So I would say that here I would take I and accumulator, and I would be integer, and accumulator would be big integer. So that's why I would need to convert I to big integer as well and multiply it by accumulator. That would be our definition of factorial for big numbers. And now we can, in fact, calculate factorial 20. In fact, we can also calculate the factorial of 200. And we can calculate even bigger factorials. So we can now do crazy things like, for example, I want to take 7, I want to calculate factorial of 7, and then I want to calculate the factorial of that again. This, of course, would give us type error because the result of factorial is big integer, and the input parameter of factorial is integer. So I would need to do integer conversion here. So you see, this is the 7 factorial factorial, 2 factorials of 7, which is pretty large number, right? So what happens if I calculate the factorial of factorials of 8? I need to scroll down. Sorry about that. So if I do that, I end up with this stack overflow exception. So why does this happen? I mean, we know that big integer can handle arbitrary big numbers, but still I get stack overflow exception. And the reason for that is the way recursion is handled. So how do we calculate recursive calls? Let us, to actually see this, let us come back to the simple definition of factorial, which is this function. And if we define the factorial like this, it will cause us the same problems. Let us have a look at it. So here is my definition of factorial. And again, in this definition, I can calculate the factorial of 7. This is it, but not the double factorial of 8. It gives us Stack Overflow exception again. So, how recursion is calculated? Let me show it using simple example. So let's calculate factorial of 5. Of course, I want the result to be 120. So to calculate the factorial of 5, I would call the factorial of x minus 1. And it would result in the call to the function factorial 4. My call would expect me to know the result of factorial 4, and then it would multiply it by 5 to get the result. So, in turn, factorial 4 would result in the call to factorial 3, to factorial 2, to factorial 1, and so on. We will go deeper into this calling stack until we reach the end. When we see that we reached factorial 1, the function would return us 1. And then we will go up, like the 1 would be returned, and at the previous level, I would need to multiply it by 2. At level further, I would need to multiply it by 3, multiply it by 4, and finally multiply it by 5 to get the result 120. However, during this recursive calls, I would need to remember the return address. I would need always to remember where to go back. And I would also need the space for all parameters, because the parameter to the function is also passed on the stack. And I need to remember those I need to remember this somewhere to multiply a number by 3, by 4, by 5. Those numbers also occupy memory. And that is why each time I go deeper into recursion, I waste some kind of memory on the stack. And this is exactly the reason why I get Stack Overflow exception at the end. So what would be the way to deal with that? Because normally, if we use traditional non-functional programming language, of course, we would be able to calculate factorial using normal for loop with just one accumulator. We don't need memory to calculate factorial. It doesn't have to be like that. So how would we deal with that problem? We can deal with this problem using so-called tail recursion. So the idea of tail recursion is that we want to write a function in such a way that the function call is the last thing during our function execution. In the previous definition, what happened is that if I want to calculate factorial of 5, I first need to calculate factorial of 4, and then I need to multiply the result by 5. I need to do one more computation after the recursive call. However, if we manage to arrange the function in such a way that the last thing in the function, the very last thing in the function is making a recursive call, in this case I would not need to remember the return address, and I would not need to remember all local variables, because I would be able to reuse the existing memory which I used for the parameters of the current call. So to change the function into tail recursive function, we can use the following trick. We will introduce another parameter called accumulator here, and this accumulator would contain the initial number. It would be like a variable for our normal for loop. Normally, if we have the for loop, we will multiply it by 1, 2, 3, 4, 5. So this would be our the analog of the counter in the for loop. And what we will do, first we will start the function with this parameter being equal to 1. And then if I want to calculate the factorial of 5, I would first, what I would do, I would multiply this accumulator by 5. So here, you see, when I invoke the function, I decrease the number of x by 1, and I multiply accumulator by the current value of x. So on the first call, the accumulator would be equal to 5, and the parameter x to 4. Then, if I do the next call, I would multiply accumulator by 4, which would give me 20 in the accumulator, and x would be 3. Then 60 in accumulator, and x would be 2, and then finally 120 would be the value of accumulator, and x would be 1. So here now I have the value of my factorial calculated already. I don't need to do anything else. I just need to take this 120 and return it directly to the calling function. And this is exactly what is written here. If I reach x equals to 1, I return the value of accumulator. So this tail recursion, because I do not need any memory, I don't need to remember return address, I don't need to remember any local parameters, it is optimized. It can be optimized into normal loop, and this is what happens with all functional language compilers. They are able to optimize tail recursion into normal loop, and that's why if I define my function in the tail recursive manner, I wouldn't need to experience those problems of Stack Overflow exceptions. Let's see how it works. So I will, what I will do, I will repeat together with you so that you remember how you can convert normal recursion into tail recursion. So first thing I do, I introduce accumulator parameter here, and then when I come to the end of recursion, I return of accumulator instead of returning 1. And inside the main function call, instead of doing post computations, I do pre-computations with accumulator. So I say x times accumulator is the new accumulator, and parameter x is x minus 1. So this function, let me start with 5 fact, and now this function fact has 2 parameters because I also need to pass in the accumulator, which is not good, but let's see if it works. I will define this and then call this. And yeah, because I use big integers, I need always to put y. So here it is. We get the number 120. So what do I do to avoid those kind of extra parameters? I would call this function fact prime, and then I will define the main function factorial. Would be fact prime, and I pass 1 as accumulator. So that would be my final factorial function, which wouldn't need any extra parameters. And by the way, because by defining those 2 functions, I would pollute the namespace. This fact prime would be another function available externally. What I can also do, I can make this fact prime internal. So I would put the fact function here. Fact prime would be an inner function, and the outer function would just call fact prime of 1. So this is the very best way to define tail recursive factorial. And now I can calculate double factorial of any number. So this is double factorial of 5 and double factorial of 8. Remember, previously we were not able to calculate that. Now we can calculate that. It would take a little bit of time, but it would not even fit on the screen. But it can be calculated, and that's great. We dealt with Stack Overflow exceptions using recursive calls. So this is double factorial of 7, just for your reference to see how huge it is, and double factorial of 8 is even larger. Luckily it finished printing here, but I think it occupied it wasted the memory of the Visual Studio Code. So again, the rules for writing tail recursive calls is to add accumulator as extra parameter. When recursion ends, you return accumulator, and you embrace the function as the inner function within the main function. The good thing is that you do not always have to write tail recursive calls, because normally you would delegate that to just one function like iter, and then all the rest would be based on these iter functions. So once we write iter function in the clever way, we would be able to define powers, factorials, and all the goodness of many mathematical functions that employ loops using this iter. The good thing is that we can write iter in the tail recursive manner without using traditional accumulator approach. It is a kind of special function because we already have this initial number I from which we start calculations. So let me start with the traditional definition of iter, which is not tail recursive. Let me just make sure that it works. I will define factorial as iter multiplication 1 1 and factorial of 5. Yeah, that works. So what we can do, what happens here is that when a is more than b, we return this number I, initial number from which we start, and on generic iteration we first call iter and then we apply function f. So what we need to do to make this call tail recursive, we need to first apply function f and then make the call. So how do we do that? Well, that's very simple. The function iter starts computation from the value I. So this value I essentially is the accumulator. So what we can do here, instead of I, we can put here the f of a and I. So the first thing I do, I apply the function f to the current counter and accumulator, or in the beginning its initial value. And this makes our function tail recursive. You can see that it still works. The only thing is that we change the order of the function applications, because in the previous definition, if I did iter from 1 to 5, what I would do, I would first apply number 5, apply the function to number 5, then to number 4, then to number 3, and so on. Here the first thing I do, I apply the function to the first value of accumulator. So it would compute f of initial value and 1, and then the resultant 2, and the resultant 3, and so on. It would in fact be more natural way of computing the numbers. And the same, by the way, is true for factorial. It changes the way factorials is multiplied, because if we do recursive calls, we multiply it first by 1, 2, 3, 4, 5, and with the accumulator, we first multiply factorial by 5. So this is quite interesting, and we will come back to this different order of computation when we talk about lists and tail recursion in lists. But for now, the important thing is that once we define function iter in the tail recursive manner, we don't need to always do this difficult exercise of defining recursion in tail recursive way. Okay, that was a very important notion, because in functional programming, if you want to be effective as imperative programmer, you always need to keep in mind this importance of tail recursion. Now let's move to and talk about lambda-calculus a little bit. And in particular, let's talk about reduction. So I would start with this simple example. So we would have this lambda expression, and the meaning of this expression is that first of all we have lambda f lambda x f of 4x. So it's basically applying function. It's a function which takes in the function f and the argument x and applies it to each other. And the second argument is lambda y lambda z plus zy, which is essentially a plus function. So, and then I pass this plus function to the first function, so it should go instead of this f. So this f would become plus, and x would become 3. So it's actually would compute 4 plus 3. That is the essence of this expression. And if I want to reduce it in the formal way, how would I do it? Well, I would notice that it consists of two applications. In particular, this is the first application and this is the second application. So I can start by taking first application and doing beta reduction, applying this application. So to apply this application, I need to take this argument and put it here instead of f. So I would end up with this expression lambda x, and then I would have this would be my f. And I would need to apply this to 4 and x and 3. So this would be the result of the first beta reduction step. And then I can notice that this beta reduction step also consists of several applications. For example, I can start using this application. So for this application, I would need to put 4 instead of x. Right? So it would leave me with lambda y lambda z plus zy and 4 3. Finally, here again I have two applications. I would reduce this one. It would give me lambda z plus z4 applied to 3. and I would end up with plus 3, 4. And then probably if I do one more reduction step, which would not be beta reduction, it would be some other type of reduction, I would get the result 7. However, because I have several applications, I can also start with different application in the first step. So what I can do here, I can the first step would be the same, but then when I arrive to this step, instead of taking this whole expression and applying beta reduction to the whole expression, I can apply beta reduction to this inner expression, right? To plus yz plus zy. And because it is applied to 4x, I can apply it to 4. And it would give me a different expression. It would give me lambda x plus z plus z4 applied to x and 3. And finally, if I do all the reduction steps correctly, I would arrive to the same result, plus 3, 4, but in a slightly different order. So what I mean to say here is that you can reduce any expression in more than one way. Well, not any expression, but sometimes expression can be reduced in more than one way. And in this example, if we reduced it differently, we arrived to the same result. And this is quite good, because it would be very strange if the expression could be equal to different things depending on how we simplify it, right? It would not be good. So the question is it always the case? Let's talk about that. So the part which we reduce, which are underlined here on the slide, they are called redexes. So redex is the part of expression to which you apply a beta reduction step. And if you have some expression, you can define so-called inner redexes and outer redexes. So the inner redex is the redex which is contained inside some other redex. And if we go further, we can arrive to the definition of the innermost redex. So innermost redex is the smallest one, but there could be several of them, just because the expression can be arbitrarily complex. So we can, for example, we can take for reduction left innermost redex. Or we can take outer redex. Outer redex is when we take as big expression as possible for reduction. And of course we can take any other, if there are multiple redexes, we can take any other redexes. But those two cases, like outer redex, leftmost outer redex and leftmost inner redex, those are important reduction cases. So why the order of reduction is important? Why are we talking about that at all? Well, let's take one more example. Let's consider this expression here. Lambda x, lambda y, y applied to lambda z, 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 lambda z, z, z. And what's the meaning of this expression? This expression, lambda z, 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 is the very notable, interesting expression, because if you reduce it, it can be reduced to itself. Indeed, if we take the second expression and put it instead of z in the first expression, we end up with exactly the same expression, right? And what it means that this is infinitely reducible expression. If we try to reduce it, we will end up into endless loop. And what is the meaning of this first term, lambda x, lambda y, y? It tells us basically take the function of two parameters and disregard the first one. Right, so if we take the function of x and y, and we need to return y, the first parameter is just discarded. And we want to compute this term applied to this infinitely recursive, infinitely loopy term. So what happens if we do, if we start reducing outermost redex? Outermost redex means that we do not reduce the inner expression, we take this whole expression and reduce it. So if we do that, of course we would end up with the expression lambda y, because to reduce this expression means put this loopy term instead of variable x. And because variable x is not present at all, we just disregard it. So in one step we arrive to the final result lambda yy. What happens if we try to reduce the innermost radix? The innermost radix here is this infinitely loopy thing lambda z z z lambda z z z. So if you want to reduce it, we arrive to the result, well, to the same result, lambda z z z lambda z z z. And if we reduce it once more, we again arrive to the same result. So if we always reduce innermost radix, it means that we will end up with the infinite loop, with the infinite sequence of reductions. If we reduce outermost radix, we arrive to the result. So this is kind of the case where we do not get exactly the same result. Well, we do not get different results also, because in the second case we just don't get any result, we get infinite loop. So it looks like the order of reduction can be important. Those two particular orders of reduction correspond to very specific cases. The first reduction, which is called, like when we consider outermost radix, like the biggest expression to reduce, is called lazy computations, or call by name, because we do not compute the argument of the function. You can imagine that reduction corresponds to the function call, because we take the parameter and we put this parameter instead of variable in the lambda expression. So if we reduce outermost expression, it means we do not reduce the arguments. We take the arguments and we put them inside the function, and we reduce them only sometimes later. So this is lazy computations. If we reduce the innermost radix, if we try to reduce everything which is in the argument of the function, it is called eager computations, or call by value, because we first compute the value of the argument and then we pass it to the function. So those are two most important reduction orders. The leftmost of inner radixes, it's called eager computation, or it's also called applicative reduction, applicative computations. And it corresponds to how normal programming languages behave. For example, in C, if you call function, all arguments of the function are evaluated first. So this is eager computation. The same, by the way, is true for F#. The other way, if we want to reduce the leftmost of outer radixes, this is called normal reduction, or lazy computation. And this is the way some other functional languages are implemented, for example, Haskell. And as we have seen in our example, applicative reduction resulted in infinite loop, and normal reduction gave us correct result. So this kind of lets us think that normal reduction is kind of better. Let's consider one more example. In this case, nothing would go wrong, but it is this simple example: lambda x plus x applied to 2 plus 3. So we would end up with the number 10. So what do we do if we do applicative reduction? We first compute 2 plus 3, the argument. We reduce this to 5. And then we substitute 5 into x plus x, and we end up with 5 plus 5, which means 10. What happens if we calculate the same expression using normal reduction? Well, we need to substitute argument into x. So we would end up with this expression, 2 plus 3 plus 2 plus 3. And when we start further reducing it, we would end up computing 2 plus 3 twice. This is an important notion, which is called a split problem, because if we have an argument which is expensive to compute, and if we do the substitution, if we put it inside the function in the uncomputed manner, it can result in several computations, because this argument can happen in several places inside the function, which is quite likely, because normally if we pass an argument, we use it several times inside the function. So this is not good. And not good in terms of performance. It will arrive, of course, to the same result, but in terms of performance, we would end up doing the same computations again. So there are some ways, there need to be some ways to avoid it. So for example, if we implement real programming languages based on this lazy computation strategy, it means that we would need to somehow either remember those computations, which is called memoization. If we memorize things, we need extra memory to remember which expressions we have already compute, so that we don't recompute them again. Or we can do so-called computation with context. We introduce kind of additional variable names for that. Or we can use graph reductions. This is very convenient way if we represent expressions as the tree in memory, in which case 2 plus 3 would be represented by part of 3. And each time we use this 2 plus 3, we provide the link to this part of the tree. In this case, if we reduce the tree in memory, next time the link would point already to the simplified result. And this is kind of strategy originally used in Haskell for lazy computations. The good thing, so we have seen that normal computations, they are in a way, normal reduction in a way is better, but it results in more problematic implementation. So why is it better? Because in fact there is a theorem called standardization theorem, which says that if there is an expression e and it has some normal form n, and by normal form we mean such form that cannot be further simplified, cannot be further reduced. So if it has some normal form n, then if we are using normal reduction on each step of the computation, we would arrive to the normal form. Well, to state it more precisely, if e has the normal form n, we would arrive using beta reduction with normal reduction at each step. We would arrive to some expression m, which would be the same as n up to variable names. This is important thing because sometimes we can end up with different names for variables in lambda expressions, and that's okay. But essentially, expressions equivalent up to variable names is called alpha equivalent, and they mean the same. So to simplify this theorem, it means that if we use normal reduction step, nothing will go wrong, and we will arrive at the result. And if you want to further dive into the proof of this theorem, I have the link here on the slide. You can dive deeper and actually see how it's proved. So lazy computations guarantee that everything is reducible. Applicative reduction order does not guarantee it. There is a subset of functional programming called total functional programming, which in fact does not, which is such a subset that even applicative reduction always produces the result. And to do that, we need to guarantee ourselves from some kind of endless loops like we've seen before. And in fact, in total strong functional programming, we demand that all functions are defined on all values. So all functions are well defined, and there is only one specific type of recursion which is allowed, called structural recursion. And the good thing about structural recursion is that on each recursion step we make the expression shorter, which means that we guarantee the absence of those kind of endless loops. Total functional programming is not Turing complete, so that's why it's not used in practice. And the reason it's not Turing complete is because it's impossible to write a program which would go into endless loop. And of course, in the Turing machine, it is possible to produce the endless loop. But in total functional programming, the good thing is that any expression is computable using any reduction order without any problems. However, when we talk about real programming languages, we definitely want them to be Turing complete, and that's why we, in most of the cases, need to decide which kind of reduction order to choose. There are some programming languages which rely on eager computations, notably F# and the family of ML languages like OCaml, Lisp, and so on. And those languages are definitely more efficient. They are easier to implement because we don't need to hold computations off until some later time. And they are much easier to implement as multi-paradigm languages because eager computational eager computational strategy is typical for normal imperative languages. So the call in F#, for example, is very similar to the normal call in C#. it's not different in many ways. So, and that's why it's easy to call F# function from C#, C# function from F#. It's kind of the same calling strategy. With lazy functional languages, it is not the same. So the most well-known example of lazy functional languages is Haskell, and it is in a sense much more elegant. You've seen that the normal reduction is the order which always gives the result. It's more elegant. You can, for example, define the if operator as a function, because you would just pass arguments, and if you don't need to compute it, it's not computed. In many ways it's more elegant, but less efficient and less interoperable. We will talk more about Haskell and lazy computations at some point in the future as well, so that you have the taste of different families of functional programming languages. But for now, we will stick with F# and with eager computations. One more thing is that one more good thing about eager computations, why they are simpler to understand for imperative programmer, is that whenever you write computational steps, things are kind of computed in the same order. Like if you say let x equal something, let y equal something, it computes those expressions as they are executed. In lazy functional languages, if you write something like that, it means that they are not computed. They are just remembered somewhere, and sometimes when you use this variable, the expression will be computed. So if you, for example, do some kind of interoperation with console, you don't have any guarantee that operators will be executed in the same order. In fact, there are specific constructions and ideas which need to be put into lazy programming language to handle input-output in the correct order. You would need to wire input-output using some additional machinery to specify this order of computation, so that it's not dependent on the structure of the program. So now we have talked about reducing lambda expressions. We know that any functional program can be represented by a big lambda expression, which is reduced up to the certain value. However, we haven't talked about implementing recursion. Recursion is not easy to implement in lambda-calculus, because to make a recursive call, you need to name a function. You need some mechanism to say this is factorial, and I want to call factorial function from inside the function, right? However, in lambda-calculus, there is no such thing as naming a function. You just have an expression, and all functions are nameless. They are all anonymous. They are all lambda expressions. And this let construction doesn't help, because let construction is the syntax sugar for lambda expression, as we have already talked in the previous lecture. And in let, the expression cannot contain the same variable, because of the way it's constructed. So we have no obvious way to define recursion in lambda-calculus. So let's talk about non-obvious way. How is it done in mathematics, in lambda-calculus, and in functional programming as well? And let's again take a factorial as an example. So let me define the factorial in this manner. Just for simplicity, I write the normal if operator. And again, to make it closer to lambda-calculus, let me introduce this kind of conditional operator. So conditional operator would take condition and two expression. One, it would return if the condition is true, and then the rest it would return if the condition is false. So this is the same definition. Instead of this let with the x parameter, I wrote the lambda expression completely. So you can probably understand that that's the same. So now let's. The problem here is that this is not exactly a good equation, because it does not define fact. I have fact present here in both left and right side, which is not good, because it doesn't look like a definition. So in fact, it looks more like an equation, right? So if I write this kind of text, it probably means that fact is a variable which I need to find, like x in the equation or something like that. So what I can do further to simplify this, let me do one clever trick here. Let me write this body of the factorial function as lambda expression. I would replace fact with the name f, and I would make it a lambda expression on this name f. So to make this expression equivalent to the previous one, I need to apply it to the fact. So you can see that if I do beta reduction here, I would arrive to the previous step. So this step here is equivalent to what is written above. We just need one step of beta reduction to arrive to the line above. However, why do I want to do that? Because now I have written this function fact as an expression which has the form fact equals some big lambda expression f applied to this fact. Right? That's what you see. This is big expression f. This is f. So in fact, what I ended up with is an equation which says that fact equals to f of fact. And this is so-called fixed point. Right? The definition of fixed point is like fixed point of a function f, big F, is the value which is not changed by applying the function. Right? If you apply f to this fact, it gives you back fact again. So this fact is called the fixed point of big function f. So suppose there is a magic operator. Just suppose for the moment a magic operator called y, which is called the fixed point operator, which would take any function f and it would return me the fixed point. So this y operator would yield this property, yf equals to f of yf. So again, for any function f, it gives me the fixed point. I don't know at this moment if this operator exists, but if it exists, then to define the factorial, I would say that factorial is the fixed point of the big function f. Right? And that's it. I do not need any kind of recursion or naming. I would say, okay, the function factorial is exactly this. And I do not use names. I just put the f inside instead of the fact. I make lambda expression around it, and I apply fixed point combinator. This is what happens when I use let_rec. In fact, let_rec adds this fixed point combinator to the function. Now the only question remains whether this fixed point combinator exists, because that's not obvious. And how do we prove that it exists? Well, the good thing is that we can write it just like a lambda expression. This is the fixed point combinator. There is one important thing here, is that when we talk about fixed points, the function can have infinitely many fixed points. For example, the function lambda_xx has many fixed points, infinitely many fixed points. Any number is the fixed point of this function. However, if we want the operator to return one fixed point, we need to specify which fixed point it returns. And yf, we wanted to return the least fixed point. And what do we mean by least fixed point? To define least fixed point, we need some kind of order on the set of functions. And I think this goes beyond our scope of our course now, because to define this order, we would need to talk about more complex mathematical conceptions, and I don't want to go into details now. Just keep in mind that we want to return one fixed point, and this fixed point is least possible fixed point. So that's why y is called least fixed point combinator. And how do we prove that this combinator is the fixed point? Well, we just take it and apply it. We write yf, we put this horrible expression and apply it to f. So how do we apply it to f? Because it is the lambda expression which has h as the parameter. We put f instead of h, and we end up with the expression like this: lambda x f of fx, lambda x f of xx. Now, what we do here, we again apply beta reduction. So we end up with the expression like this. And you can see here that we end up exactly with f of yf. And this is the definition of fixed point, right? It is not changed when we apply f to yf. So, luckily, we were able to write explicitly the fixed point combinator, which allows us to define recursive functions in lambda calculus without naming. This is great, but you may ask, how does it refer to F#? Can we somehow use it? Does it make any sense at all? Well, in the moment we will see that you can in fact write functions in the same manner. Let me show you an example. So here I have my factorial definition written in exactly the same way as on the slide. So I can make sure that this in fact gives me factorial of 5 equals to 120. Can I write it using fixed point combinator in F#? Well, yes, sure I can. So here is the definition of fixed point combinator in F#. I say let rec y of fx equals to f of yf of x. Indeed, that is a little bit different definition, but that's the one that works in F#. So how do I write this into the fixed point definition? So first of all, I write it. I put the argument here. So I say function of n, and I remove n from here. This is pretty much the same factorial as before. Let me make sure that it still works. Okay, now remember, what do I need to do to make it definition using combinator? I get rid of recursion because it's not recursive anymore. All recursion is handled by y combinator. And in the argument of y combinator, I make this lambda expression with some function f, which I use here instead of my factorial. And I put one y combinator on top. So I define this, and I end up with the same result, 120. So you see, the beauty of F# is that I can even put the concept of recursion into some other function. So y, you can say y is a kind of function, right? Even though it's called combinator, but you can consider it as a function which takes an argument and it makes this argument recursive. And it's kind of magic, because I can put even the conception of recursion I can factor out into a separate function, because now this fact is not recursive anymore. Y is defined using recursion, right? So I do need to have recursion somewhere. Yeah, this is how recursion is defined in programming languages, in the functional programming languages. So why do we call y combinator a combinator? What is a combinator anyway? So combinator refers to the lambda expression without any free variables. So if we look at the y combinator here, this y combinator doesn't have any free lambda variables. So it's kind of closed lambda expression. And that's why it's called combinator. One example of combinator is y combinator, which we know, the recursive combinator. There could be other different combinators. For example, I can identity function lambda xx is a combinator. In the expression lambda xx, there are no free variables. And this idea of identity function, well, it is the idea. It's a pure function. You don't need to compute it. It's just the idea of something which does not change the argument. I can have another combinator which is called k. K is called cancellator. And the idea of it is that it's defined as lambda x, lambda y, x. And the idea of it is that if I, for example, compute k of 5, it gives me the function which returns 5 regardless of the argument, right? So it kind of cancels the argument and returns the value. And then there is another combinator which is called S combinator or distributor. And the idea of S combinator is kind of clever composition. It takes functions f and g and then argument x, and then it computes f applied to two arguments, to x and to g of x. So it's called distributor. Those combinators can be defined, in fact, if we consider the definitions without lambda expressions, but using let operators, and they can be defined in this way. I can say I of x equals x, k of xy always equals x, and s f g x equals f of x, g of x. And you can define this in F# using exactly the same definitions. So what's good about combinators is that in fact you can build the whole theory similar to lambda calculus based on only combinators without lambda expressions and variables. And this is kind of cool because in lambda calculus we have two basic operations. We have application and abstraction. And application involves variables. In combinatory logic, which is equivalent to lambda calculus, we have only one operation. We have just application. And we have just combinators and application of combinators to each other. And this is very cool. And it turns out that any function can be expressed by using combinators in a variable-free manner, without any variables, just by application of different combinators. To give you an example, we can, for example, express the identity function as the combinations of s and k. And this is kind of not obvious why is it like that, but we can verify it. If we go to this our F# console, we defined I, k, and s. And now let's just take skk and apply it to 5. And the result would be 5, which means that we indeed ended up with identity function. We can prove it, that is I equals to skk in the formal way. We can just put definitions of s and k into this expression, perform a series of beta simplifications, beta reductions, and we would arrive to lambda xx, which is indeed I. I would not go into detail, and you can, if you want, you can try to follow those computations yourself. So in fact, we can say that the minimal set of combinators that can be used to express any function is called basis, and s and k actually forms the basis. And in fact, what you can do, you can build the whole programming languages just on 2 operators, and that's it, and 1 application. This is very beautiful, but of course it's not very practical because all the computations would be rather long, but in theory, this is, I think, the great result. So let's see this magic in action. Suppose I want to define factorial based on combinators. I would take, to simplify things, I would use a few additional combinators. I would use combinator C, which swaps the arguments of a function. So if I have the function f, which has argument g and x, c of f gx would call f of xg. So basically it takes a function and swaps its arguments. And then I would use y combinator, and I will also use one more combinator for conditional operator. So this would be a rather clever conditional operator. It would take the predicate predicate p, and 2 functions f and g. And if I apply this conditional operator to x, it would compute p of x. And if p of x is true, it would return f of x. Otherwise, it would return g of x. So not exactly the very traditional conditional operator, but slightly modified one. And I will show you now that the factorial can be written using those combinators in this manner as you see here on the screen. This is kind of not obvious. How can you do that? Let me show you step by step how we can do that in the F# interactive. So here I have my original factorial definition and the definition of my combinators. And combinators S and combinators S and K we have defined above. So let me copy this over. I will start with this definition, and I would always verify that factorial of 5 is 120. So this is correct. Now, the first thing I do, of course, is I apply fixpoint combinator. I have already done that, so to do that, I get rid of recursion here. I put one y combinator, and I make this the function of f and n. And instead of fact, I use f. This is equivalent, and we have already done this change, right? So now I have this function. What can I do to start replacing things with combinator. First of all, let me replace if. So here the if looks like that. If n equals to 0, then I want to return 1, otherwise I return some kind of computational thing. So this can be replaced by conditional. So conditional takes predicate p, which is applied to n, right? And then it also takes two functions which are also applied to n. So the first condition should see if n is equals to 0. So I can write this like this. The condition would be equal to 0. Remember that I can use partial application, right? So the equality operator can take just one argument, and it would give me the function which checks if the other argument is equal to that. So this would be p of x. So it would be applied to n, and it would return whether n equals to 0 or not. Then if n equals to 0, I need to return 1. But remember that in cond, I apply this to n. So I need to return 1 regardless of any parameter. And this is exactly k combinator. So this would be k of 1, right? And then the third parameter would be the function of n, which returns this computation. So that's it. Let's see if it still gives us 120. Yeah, here, of course, I forgot to get rid of n. Now let's see. Yeah, it gives us 120 still. So this is equivalent, right? What do we do next? Next is a very tricky thing. We want to get rid of this function f here. We want to move this function of f as close to the end as possible. How can we do that? Well, to do that, we would we have this expression, and we want to move this fun f somewhere here towards the end. So how can we do that? Let's consider just for the moment this expression, lambda f g of h at f. So why do we want to consider this? Because here we have the function of f, and this function of f is exactly lambda f here. And then we have some function g, and this would be the function g, and it is applied to some function of f. This would be some function of f, which is h of f, right? H of f. So now how this left-hand side can be simplified? Lambda f g of h of f. Let's think about the idea of this expression. I want to take f as an argument, and I first compute the function h of f, and then give this as a parameter to g of f. So essentially, this is the composition of g and h, right? So it's the argument I can get rid of the argument. So I hope this is more or less clear to you. Why is this so? So in F sharp, if I want to write it in F sharp, I would write it in such a way. If I have fun f of g of h of f, I can replace it with h composition g, because h is computed first, and this is exactly the way composition is written in F sharp. Now, in my case, I have a little bit different setup. I have function of f, and then g of some expression e, which involves f. So in this case, what I can write, write this. So this is e is a kind of expression which contains f. So to make it a function of f, I need to explicitly write the lambda expression here. So I need to combine this lambda expression with the function g. So this is pretty much the same as above, just a little bit modified for the case when h of f is not explicitly a function of h applied to f, but just any expression which contains f. So now see how this can be applied here. So fun f is this fun f, g is this expression here, and what I need to do, I need to put composition here, and here I need to make this a function of f. This is kind of the equivalent modification. Let me do it now inside the editor. So fun f, I get rid of fun f, I replace it by composition, and I add the fun f here at the end. Let's make sure it still works. Yeah, that still equals to 120. Now, here I need to simplify this even further. So what happens here is that I take f and n, and I have this multiplication, n times f of n minus 1. And this, I don't know if it's obvious to you, but here I have exactly the case for distributor, for the S combinator. Because S combinator takes one function f of 2 arguments, and this would be multiplication. And then it multiplies, then it applies this function to the argument n and some function of n. So argument n would be this argument n, and function of n would be f of n minus 1. So how do I modify it? I put here, so I get rid of fun f of n. I use the s combinator instead. So it would be s of star. And then it would be applied to f and to this function. This function would be f of, so this function would be f of n minus 1. And what does it mean to compute f of n minus 1? It means to make the composition of f n minus 1. So first I would do minus 1 and then f. And how do I compute minus 1? I put minus 1, but I need to swap the arguments, because if I just say minus 1, then the last argument is substituted by 1. So that would be the expression that I have here. And yeah, I in fact forgot one thing here, is that the f here is not defined, because I forgot to have here the function of f. So now this gives us, it gives us, it should give us 120, but I put an extra bracket here. Yeah, so now this equals to 120. So we have the equivalent expression here, and we need to get rid of f to move this completely to combinators, right? How do we do that? You can probably recognize we have the similar problem here as we had before when we moved fun f through those conditions. So using the same approach, we have here fun f and then a number of functional application. So we get rid of fun f here, and we replace it by composition, and we move it here. This should give us again 120. Now we are very close to the end, right? We just, what can we do here? We have a function of f and then a composition. So what does it mean, a composition? Composition first takes this c and then f. I can in fact write it in such a way as to put c minus 1 first and then f. Now this brings us even further to the result. Now I can write composition as the binary operator. So here I would say c minus 1 is the first argument, and here I would have composition, correct? And this is exactly the case of partial application, right? So I can get rid of fun f, and I can get rid of f here. And this is my factorial written without any lambda expressions, without any variables, just by combining combinators. I think that's really cool. That shows you the essence of functional programming. You can write the whole program without any variables, without any loops, without any constructions, just by combining a very complex expression. Well, does it mean that you should always program like that? Of course it doesn't, because it's not very easy to understand what's written here. In fact, it's horribly difficult to understand what's written here. So in real life, of course, you want variables, you want comments, you want your program to look understandable. But it's actually the case that you can gain a lot of advantages if you start thinking in a functional way. Because sometimes you don't need to put extra variables. Sometimes you can just think in terms of combining functional constructions together to achieve required result. And in our course, we will see many examples when this can be done. In fact, the main reason that you study this course is to achieve this kind of functional thinking. So I would suggest, in fact, this was a very important and very difficult exercise. I would suggest you try to repeat those steps yourself, starting from scratch with the definition of factorial, and see if you are able to figure out all the steps in detail for yourself. And if you have any questions, you can reach out to me in Telegram chat, and more information about this course is available at the course page at my website. So, my name was Dmitry Soshnikov. That was another lecture on functional and logic programming, and I will see you in the next lecture.